we'll be having a look at combinatorial geometry in our final workshop. Let's have a look. So what is combinatorial geometry? This is quite an interesting topic. It is a hybrid between the topics of combinatorics and geometry. So as the name suggests, combinatorial geometry, we're using ideas in combinatorics and geometry in the same question. Often when you see a combinatorial geometry problem, usually the statement of the problem is posed in purely geometric terms, but however, the solution often requires a combination of both geometric and combinatorial ideas in their solutions. So in normal combinatorial problems, usually the actual statement of the problem often has permutations and combinations, for example, but combinatorial geometry is quite interesting because when you read the problem statement, it's maybe not immediately obvious that you're going to use combinatorial ideas, but often it turns out the actual solution to the problem uses combinatorial ideas. So yeah, we'll have a look at those combinatorial ideas later on. Okay, so usually in classical geometry problems, the previous workshop on geometry, often those types of problems have only a small number of points in the diagram. So for example, you might have a triangle ABC and maybe one or two circles and some quadrilaterals, for example. However, in combinatorial geometry problems, you can often have any arbitrary number of points. So you may be asked to prove it for all values of n, where n is a number of points, or if n is a number of lines, for example. So you could have arbitrarily large number of points and lines in lots of problems. That's one interesting thing about these types of problems. Okay, so first proof technique we're going to have a look at is using proof by contradiction. So this is one technique used for combinatorial geometry problems, and this example we have over here it's asking, is it possible to do this certain task over here? So you have to try to color every point on the circle using two colors, white and black. So there is no isosceles triangle whose vertices all have the same color. Okay, so you can already see, compared to regular geometry problems, this time we're actually dealing with infinitely many points on the circle. So we are all those infinitely many points on the circle, we are coloring each of the points white or black. So we have W equals white and B equals black. We're coloring infinitely many of those points white and black, and we want no isosceles triangle whose vertices are the same color. So for example, if I draw an isosceles triangle like this, whose points are on the circle, we are not allowed to have all these points being white, for example, or we can't have all the points being black. So in all these infinite points which are colored white or black, we must avoid a monochromatic isosceles triangle where all three points are the same color. So next all drawings. Oh yeah. So yeah, the first step, it's always for combinatorial geometry problems, always to draw a diagram and try to label some of the points white and black. So you can't, I guess you can't manually put infinitely many colors, but you can maybe try to put some of the colors. You can label some of the points white or black at least, and see if you can at least get it working for a finite number of points. Okay, I guess if you try for a while, you might realize that even for just a finite number of points or just a few points, you might already start to see that the task seems to be impossible because, for example, you might have a situation where you're not allowed to color it white or black. So, for example, I have two isosceles triangles. If I have two blacks here and two whites here, then you can construct two different isosceles triangles. You have two different isosceles triangles, but no matter which color you choose for this one, it's either going to be white. You're either going to have a all black triangle or all white triangle. So even for these finite number of points, it's already impossible for this configuration. So one interesting thing here is you may be able to prove it's impossible just by considering a few of the points rather than all the infinite points. Okay, so proof by contradiction is quite a nice idea here. So yeah, you can start by assuming it's possible to color every point on the circle. And now, again, just as I mentioned earlier, we can maybe consider a finite number of points and see if we can reach a contradiction just from those finite points. Okay, so since we have all the points are white or black, there'll always be two different points, A and B, of the same color. And you can say without loss of generality, you can assume both of them are white. Okay. Wait, just thinking something is missing. Wait, it's point P gone. Let's see, where's sorry, just hang on a second. Okay, so okay, so what we're doing here is we're choosing point X. So we start with points A and B which have the same color, and now we're going to consider this isosceles triangle here by making AB and AX the same length. And we can see if X was white, AXB, triangle AXB would all be white, so that's a contradiction. So this point X must be colored blue. So that's a good start. So we've just considered one isosceles triangle here, and already we've forced another point to be blue. Okay, and now we can do a similar thing, but now the isosceles triangle is going in the other direction. So now we're looking at triangle ABY, which is also isosceles if we make AB and BY the same. Okay, and again, similar to before, you can't have all white, you can't have a triangle of all white, so Y has to be blue. Okay, so remember that setup from earlier where I drew 4 points and we got a contradiction because we can't label the fifth point. So in fact, we have the exact same scenario over here. So if you make P the midpoint of this minor arc AB, so if P is the midpoint, we also have some symmetry going on. So because AX, AB, and BY are all the same. So by symmetry, we have a line of axis of symmetry like this. which means, let's use another color. So AP and PB are the same, and also XP and PY are the same. So we actually have two different isosceles triangles over here. And it turns out, if you look at the blue points, you can't have P being blue because then you have a all blue. The green triangle will be blue points, but also P can't be white because then the yellow triangle will have all white points. This means we can't give any color to P, so this is our contradiction. Oh, okay, so this you might think this completes the problem and it proves it by contradiction. However, there's a slight catch where 5 points, these points here may not all be distinct. So an example would be if it's possible for X and Y to be the same point. And that example can show that example using an, can show that example using an equilateral triangle. So if, if you have A and B, and they have this the correct distance apart to create an equilateral triangle like this, it turns out X and Y become the same point, and that's a slight issue because now you can't really make this triangle anymore because now it becomes now you just have two lines like this, so it's a degenerate triangle. So you can't really consider that as a triangle anymore. So that's a slight gap in the proof. However, one potential way of fixing the gap is you can consider one might be more way, but one way could be just to consider a small range of points on an arc and then choosing two distinct points to be with the same color. And now this can help avoid equilateral triangles from being created. So if we just consider points, if we find points A and B within a small arc range, then this can avoid equilateral triangles from being created. So that's a way of fixing that gap. Okay, it's actually I think you don't necessarily have to solve the cases separately because using something like this, you can avoid this degenerate case altogether by making sure the triangle you create is not equilateral. There's actually a much quicker solution to this question, and this uses another technique, combinatorial technique, which is the pigeonhole principle. So now if we consider five points equally spaced around the circle to make a regular pentagon, one interesting observation is any triangle involving these points, any triangle you draw will always be isosceles. So all the triangles in this diagram are isosceles. This means no 3 points can be the same color in this diagram. However, by the pigeonhole principle, since you have 2 colors and 5 points, there must be one color that's used at least 3 times. So this means just this regular pentagon setup makes it impossible to color all the points white and black. So that, I guess another thing to add is there's lots of these combinatorial geometry problems where you color infinitely many points something. So that's one example. But often these problems can be solved just by considering a finite subset of the points. So you don't have to do stuff with infinitely many points. So yeah, just by considering a small subset of the points, that's enough to reach your contradiction for a lot of these types of problems. Okay, yeah, pigeonhole principle. Okay, so now we're having a look at the extremal principle. So this is not exclusive to combinatorial geometry. This is used in quite a lot of areas. So often if you have a lot of objects, you can try to find something that's extreme in some sense, such as being the greatest or the least at some property, or the best or the worst. So if you can order something from one extreme to the other extreme, you can try to consider something of one extreme. So sometimes these extremes may not always exist. For example, there's no largest positive integer, for example. So, but there's always, in a set of positive integers, there's always a smallest number. So sometimes the extremal object may not exist, but if it does exist, then often you can consider that extremal object and often be used in proof by contradiction, as you'll see in the example question. We have a set of disks in the plane and pairwise disjoint interiors. Each disk is tangent to at least 6 other disks in the family. Prove there are infinitely many disks in the set. So pairwise disjoint interiors, that means you can't have 2 circles overlapping. And each disk is tangent to at least 6 other disks. So circles must be externally tangent and not internally tangent, because since no circle can have a part inside another circle, it means you must have something like this going on. So you have at least 6 circles tangent to each circle. So you have to prove there must be infinitely many disks in the set. And again, proof by contradiction is coming back. So we're assuming there are only finitely many disks. And now this is where the extremal principle comes in. So since there's only finite disks, we can consider a disk D of minimal radius R. So remember, if there's infinitely many disks, there may not be a minimum value, because, for example, you can converge down to some number. But in the finite case, there's always going to be a disk of minimal radius. So if we have a look at this setup over here, we're looking at the smallest disk. Okay, so I've drawn the smallest disk. And now I'll draw 6. Wait, I'm just checking. If my annotations can be seen. Any confirmation?
Yep.
Okay. Okay, there's a disk of minimal radius R. Okay. We want to place 6 more disks tangent to this smallest disk over here. But remember, since this is the smallest disk, all the disks surrounding it must be at least as large of radius. Maybe place 1 circle here, and say we attempt to place 6 circles. So okay, it's probably not the best diagram, but it turns out the best case scenario is if the circles are as squished as possible. So you can try to I guess you can try to roll some of the circles to make them squished or as far apart as possible, as close together as possible. For example, if you have two disks here, you can try to move them close to each other and make them tangent by rolling them towards each other. And it turns out the tightest packing you can have is when you have 6 disks, all of the same radius, surrounding the center disk. So you have 6 disks surrounding here, and they have, in this case, they have the same radius as the center disk. But the problem is, if you try to make any of these disks larger, it's impossible to fit 6 circles around the center disk. So it turns out none of these circles can be larger than what they currently are. That's so what that means is it's impossible to have it's impossible for any of the 6 surrounding disks to be larger than the center disk, because there won't be so this is the tightest possible packing and can't really expand any of the outside circles anymore. So that means it turns out all the 6 surrounding disks of the smallest disk must also have the same radius. So you actually have not just one smallest disk, but you actually have even more smallest disks. Okay, so it says here there's only room for exactly 6 disks, all of radius r around d. And it says if we apply the same argument to each of these disks and so on, we can expand outwards forever. So we have 6 surrounding disks here, but we can draw even more and more disks surrounding. And by the same argument, they must all be the same radius. So you'll have some nice pattern here, some hexagonal pattern of circles, and this pattern must continue forever. So that generates infinitely many disks of radius r, and this is a contradiction because we assumed it was finite at the start. But even so, the main logic here is we first assumed there was finally many disks, and considered the disk of smallest radius, but it turns out the surrounding disks must also have the same smallest radius, and you can again keep on going outwards forever to have infinitely many disks of that same smallest radius. That's the final contradiction. Okay, so now so now we have perturbation, and yes, Odin taking over now.
All right, great stuff is here. Yeah, so we've gone through a few techniques. All of these techniques are pretty different. So the idea with perturbation is that you have some configuration at points. And it's an interplay between some finite configuration of a finite number of points, lines, whatever, and also the fact that the plane has infinitely many lines, infinitely many points. This is going to allow us to, in a lot of cases, to nudge the configuration and show that it has some property in relation to some of those infinite number of lines or points. If we go to the next slide, we can start off with an example. So we have some finite number of points in the plane, and we're going to assume that there's no 3 points that lie on a single line, but there is going to be a line between any pair of points, of course. And we want to join them up in some sequence. And we want to do it in a way where we have kind of a polygonal path of line segments where the end of each segment is the start of the next one. And we don't want these to cross each other. And maybe you can have a little bit of a think about how you would do that. The way I'm going to approach this is, well, for most cases, usually you're not going to have any 2 points sharing an x coordinate if you just pick a bunch of random points in the plane. The probability of them sharing an x coordinate for most ways of choosing them is going to be 0, because there's an infinite number of x coordinates to choose from. And if they all have different x coordinates, well, you can certainly pick them such that you pick the smallest x coordinate first as the beginning of your set of line segments. And then you pick the second smallest x coordinate and you join a line segment between those two. And then from the second smallest x coordinate point, you join that to the third smallest x coordinate point, and so on. You're going to end up with a polygonal path through the plane that doesn't have any crossings, because all of these lines are increasing in an x coordinate. And if you follow the path along, you're never going to go back in terms of the x coordinate. You're always increasing. And in fact, we can also guarantee that there's no vertical lines. And the way that we're going to guarantee this is, well, if you think about the number of possible line segments between these n pairs of points, it's just choosing any pair of points, which is n choose 2 different line segments. And well, if all we need is that none of these line segments are vertical, we have a finite number of n choose 2 line segments. Vertical is kind of, 90 degrees straight up. But if you think about how many possible angles there are in the plane, well, there's an infinite number of possible angles. You have the whole unit circle full of angles. And so because we have a finite number of line segments and we have an infinite number of possible angles, even if we end up with some configuration where we have vertical line segments, we can always just rotate the configuration, and we'll always be able to find some angle of rotation where the configuration has no vertical line segments. And in that case, the polygonal path we get between the points, just labeling them in order of the x coordinate, is going to be very nice. It's going to be consistently increasing as we travel through the points. And this gives a very nice construction that satisfies the criterion we wanted. Maybe we'll move to a different example. Or I think there's an example of perturbation in the problem set, hopefully. So you can give that a go. Does anybody have any questions about perturbation, about that technique? Awesome. So we'll move on to induction. Induction is a very versatile technique, of course. But often, if we want to prove something in the general case for, n points, n line segments, this can be a helpful technique where we build up from a smaller case. So we'll take a look at this problem. We have some fixed number of points in the plane, 1002 points. And again, we're joining them with line segments, although this time we don't need a path, we just need line segments between each point. And we want to take the midpoints of these line segments. Of all the line segments between the points, we take their midpoints. And we want to show that we end up with at least 2001 distinct midpoints in this configuration. And the way that we'll prove this is, instead of considering 1002 points, we'll consider n points. And we'll build up from the very simplest case of n equals 2. And we'll show that every time you add a point, it has a very specific effect on the number of distinct midpoints that you can have. So certainly it takes a little bit of fiddling around, I guess, to get this 2n minus 3 quantity. Certainly when you plug in 1002 as n, your 2n minus 3 is going to be greater than 2001. In fact, it's going to be exactly 2001, which is convenient. And certainly in the n equals 2 case, we're going to have 2n minus 3 being 1. And of course, we're going to have one midpoint because there's only one possible line segment. The tricky thing is when you get multiple line segments, it's possible that 2 of them could share a midpoint, 3 of them could share a midpoint, and that would reduce the number of midpoints you have, which would not be so good. So we'll start with the n equals 2 case. And we're going to use a strong inductive argument in the sense that we want it to be true for all the smaller cases, not just the next case down. So we're going to assume it's true for 2 through m, where they're all an integer number of points. We're going to assume that this property about the midpoints holds true. And then we're going to expand that hypothesis to the m plus 1 case. And so if we have m plus 1 points, again, because of the argument from before about an infinite number of angles and a finite number of line segments, we can certainly arrange the points so that they all have different x coordinates again, in the same way that we did last time. And if we label these again in order of increasing x coordinate, hopefully that will make them a little bit easier to think about, because now we just have a nicely ordered sequence of points. So we know that for every configuration of m points, we're considering this m plus 1 configuration, but of course the m plus 1 configuration has a whole bunch of configurations within it that are just m points. And we know how many distinct midpoints they have. We want to think about how many distinct midpoints can this new larger configuration have. So if we move on with this proof, we've ordered these points in order of x coordinate. And we know that there are 2m minus 3 midpoints because we have, for example, the first m points have 2m minus 3 distinct midpoints. And we're you can think about the furthest point to the right with the highest x coordinate as your new m plus 1th point. If you think about the line segment between your mth point and your m plus 1th point, well, all the other points have a smaller x coordinate than the m plus 1th point and the mth point. So that line segment between those two largest points is not going to cross any of the other points to the left of it. So that certainly has a distinct midpoint. And also we can see that the line segment between m minus 1 and m plus 1, the line segment between those points it's not going to be the midpoint of m minus 1 to m, because if it was, m minus 1 to m and m-1 to m+1, they share a point. I might annotate this. So we've got, this is m-1, m-1, and this is the mth point. This is the m+1th point. We've certainly got a new midpoint here that we haven't seen before. And this line here, well, this diagram I've drawn is a little bit deceiving because that could intersect with this line segment here, but it's certainly not going to be the same line segment. If it was the same line segment, then m and m+1 would be the same point. We wouldn't have m+1 distinct points. We would just have two copies of the mth point. So these aren't going to be the same line segment. And obviously this line segment here is to the right of all the other line segments in the configuration. So we now have two new midpoints that we haven't seen before in the first m points. And because of this, we can conclude that there's two extra points added by this m+1th point, two extra midpoints, or two extra red points. And if we rearrange this a little bit to be in terms of m+1, we can see that we get the same kind of expression, but in m+1 instead of m. And if we continue this upwards with a strong inductive argument that we've built up already, this shows it for everything, which also shows it for the special case of 1002 and 2001. Yeah, so if the x values are the same for m-1, m, and n+1, we can use the perturbation argument from the previous problem to sort of nudge the configuration around such that none of the n-2 lines are vertical, because there's an infinite number of possible angles that the configuration could be rotated at. You can always guarantee that you're not going to have some 2 points that are on a vertical line and share the same x coordinate. So that perturbation argument is what lets us assume that the x values are distinct. Does that make sense? Cool. All right. I think we will now move on to the next technique, which I believe is convex holes. Ethan, are you good to present that bit?
Yep.
Cool.
Beautiful. Alrighty. So hang on. Can I annotate still? I can. Perfect. All right. So to begin with, we're going to start discussing kind of what convex holes are, and then we're going to have a bit of a look at kind of where they're useful in combinatorial geometry. So if you had some kind of wooden board, so I mean, I suppose you could have some kind of plane, and you hammered in some nails, right? So you could have like something like this, and then maybe one over here and one over here. If you took a rubber band and stretched it around the entire area, it would kind of contract around everything, and you would end up only really kind of touching these 4 points here. So these kind of points in the middle wouldn't really be affected by your rubber band. And you end up with a polygon whose angles are all less than or equal to 180 degrees. So this is a convex shape, effectively, which means that all of the angles on this kind of outside here, none of them exceed 180 degrees, because otherwise you would have your rubber band kind of dip in and then come back out, and that's impossible, right? So this is the idea behind a convex hull, right? So the region occupied by this polygon, so this kind of part here, is called the convex hull of the points, right? And there's a few kind of different ways you can define this. So to begin with, we can define it as just kind of, okay, you can define it abstractly and more concretely. So more abstractly, we can begin with the definition of a convex set, which is if you have some kind of set and you can take any 2 points and join them by a line, and that line is entirely within the set, then we call that set a convex set. If you had something like this would not be a convex set, because if you took this point here and this point here, and you drew a line between them, this little bit here leaves the kind of set that we're dealing with, right? So this here is called a convex set. And more abstractly, a convex hull is the set of points is defined as the intersection of all convex sets containing T. Now that's a little bit of an abstract definition. You can kind of, I suppose more intuitively, it's just if you kind of take all the points and then you kind of like draw a bunch of lines between them and then filled in everything you could. So you draw every line between all of the points you can, and there's a bunch of them, and then you just fill in all the spots in between. And that's kind of a more constructive way to define the convex hull. But generally, we won't really need the definition of a convex hull. We'll more be looking at these kinds of properties. The fact that it's a convex set means that between all of these points, the angle is less than or equal to 180 degrees, right? So let's take a little bit of a look at an example. So we have a set of 5 distinct points in the plane, and we want to show that there are 3 points, A, B, and C, such that this kind of angle inequality is true, right? So if we were to draw 5 points in our plane, that's not 5, is it? That's 6, sorry. Yeah. So if we were to draw 5 points in our plane, it is possible in our first case that doing so gives us a kind of, our convex hull ends up being the entire thing, right? So if it's 5 points forming a convex pentagon, then the angle sum of the pentagon is 540 degrees, and at least one of them must be between kind of 108, which is the regular polygon, and 180 degrees, right? So if you have a regular polygon, all of the angles are going to be 108 degrees. And if you had, say, a regular polygon, this isn't going to be regular, but pretend it is. If you had a very dodgily drawn regular polygon and you kind of made one of them a little bit sharper, in making this sharper, because the angle sum is 540 degrees, you're making one of them larger, right? So this becomes closer to 180 degrees in kind of compensation for this decreasing in angle. Effectively, no matter what you do, any kind of angles are going to sum up to 540 degrees, and all of the terms must then be, or at least one of the terms must then be between 108 and 180 degrees. So in this case, it works out perfectly fine. However, when we're dealing with convex hulls, it is not necessarily the case that we always get all 5 points in our perimeter, right? So it is possible, for example, in the second case here, that only 4 of them kind of end up being on our perimeter, and this last little point ends up being somewhere in the middle. So to deal with this case, we're going to be going by cases. So to deal with this case, we can divide it into 2 triangles, and then take a look at where this kind of point can be. So the point can be in the interior. So the 5th point must be inside one of the triangles. So it must be in the interior of one of these triangles. And I'll deal with the extra case that you might have noticed in a second. So if it's in the interior of the triangles, then we can break up this triangle, right? If we take a look at the 3 angles around it. So effectively, we've kind of reduced the problem to something like this, yeah? And if we draw lines here, then we can look at these 3 angles around the point in the middle. And we know that the sum of those angles is 360 degrees. Each of them is at most 180 degrees, because if it were larger than 180 degrees, we'd have to have something like this, which would kind of get us outside of the triangle, yeah? And they add up to 360. So one of them, one of the angles in there is at most 120 degrees, right? And we're going to have, so we can find an angle that is at most 120. I think at least 120 is what we're going for there. So we're going to have one angle that is at least 120 degrees and at most 180 degrees, which is certainly within this kind of range here. Now, there is one extra case that isn't mentioned on the slides, which is if we were to have our quadrilateral like this, and it just so happened that the point we defined was right here, then we do have a slight issue because it's no longer kind of in any of the interior of our triangles. Good thing about this case, of course, is that we have exactly the same argument now around the midpoint here, except now we have 4 angles, right? Which means that our angle sum is going to, so how do I go? So we've got this point here. Now we can't deal with the angle sum here because it could be the case that the angles around there are 90 degrees, right? But we know that at least one of them is at most 90 degrees, I think we're going for.
I think one angle will be exactly 180 degrees. That's
Oh, yes. Okay. So if you break it down, yeah, sorry, my bad. So we've got, say, a point on our angle here, then this angle here is 180 degrees. So we're fine because we have equality with 180. That's good. Yep. So that case there is dealt with. And the last case, or not necessarily the last, but kind of the last important case, is this one over here with the kind of triangle. So if our convex hull has 3 points on it, then we can kind of have the same argument. We know it's going to be in the interior, so we can reuse our argument and only consider one of the points, ignore the other, and then we've got our little angles around the middle, right? And then finally, if the convex hull ends up being a line segment, that would mean that all of the points are collinear. So you have 5 points in a line, in a bad line, but a line all the same. And then you could take any 3 collinear points on the kind of interior, I suppose. So these 3, or you could choose these 3 if you wanted, and they would form 180 degrees by necessity, right? Yeah, so we're kind of dealing with convex hulls as looking at the angles, right? So the points involved in a convex hull, we know information about the angles, and by kind of breaking it up into smaller shapes, we can deal with those shapes separately to bound whatever angles we need in the whole problem. Any questions about convex hulls or anything like this before we move on to the next one? Doesn't look like it. Cool. Alrighty. So the next thing, as mentioned earlier, pigeonhole principle does show up quite a bit. So we're given 6 points inside an equilateral triangle of area 4, and we want to prove that among the 9 points, so the 6 points that we've got and also the 3 that are included in the equilateral triangle, 3 of these form a triangle of area at most 1, right? So what we can do here is divide the triangle up into 4 equilateral triangles. So if we had our equilateral triangle, a kind of, I suppose, a very standard construction in mathematics is to kind of break this equilateral triangle up into 4 smaller equilateral triangles. And because they're all congruent, we know that they all have the same area, which is 1, right? And then we can apply our pigeonhole principle. There are 9 points. I'm going to have to, I'll redraw that. There are 9 points, and there are 4 kind of triangles. It is the Triforce, yes. It's my favorite kind of triangle. So we have 9 points, and there are 4 kind of parts they can be in. They can be in the top, bottom left, bottom right, or in the middle somewhere, right? So if we were to put them in the triangle somewhere, by the pigeonhole principle, we must have at least 3 in one of the pigeonholes, right? So if we tried to very evenly distribute things, we could have maybe 2 over here, maybe 2 here, 2 here, 2 here, and then the last one would have to kind of fill in one of them, right? So one of the triangles here of area 1 has a smaller triangle within it. So because we've got a triangle within a triangle of area 1, we've kind of formed a triangle that has area at most 1, and we're kind of done. However, we could have things on the boundary. It doesn't really affect the argument because you still effectively have the same kind of construction. If you have a triangle and you've got points on the boundary, then you still kind of have a triangle contained within another triangle. You could even, in like the worst case, have your 3 points be actually the same as the vertices of this smaller triangle, right? In which case, it's exactly 1. But in either case, we have area at most 1, which is what we want. But we can actually sharpen this a little bit if we do a little bit of extra work, right? So we can sharpen the result from area of at most 1 to area of at most 4/13. And to do that, we have to kind of go, it's a slightly induction-like argument. So to do this, we use some information about the points themselves. Instead of subdividing the triangle, we subdivide it based on each of the points. So the first thing we do is we take our original equilateral triangle and we take the first point, whatever point it might be, and put it in. And then we subdivide the triangle based on it, right? Like that. So we've now chopped our original triangle up into 3 smaller triangles, right? And we can continue doing this bit by bit. So the second point, and I'll redraw this, the second point is going to subdivide, say, if we put it here, yeah? If it was here, then we've got a smaller triangle that we can subdivide even further. And what we've done here is we've turned one larger triangle into 3 smaller triangles. So the process of going from this to this adds 2 triangles, right? And the process of going from the big triangle and subdividing it into 3 also adds 2 triangles. And if we continue this process, each step of the way, we're going to add 2 triangles, right? So if we start with 1 triangle, and each point that we add, all 6 of them adds 2, we have 13 triangles in total. So we've subdivided the larger triangle into 13 triangles. So at least one of those must have area at most 4/13. So we've kind of cut it down quite a bit. That's less than a half, right? There is also one other point, which is, once again, you will have to consider the boundary. If we were to have our, say we had our original subdivision, stuff like that, and then when we went to add in the next point, right, it was, say, on this boundary here, right? Then we can't exactly break up one triangle into 3 different parts, but we can take this triangle and cut it in 2, and this triangle and cut it in 2, and we've turned 2 triangles into 4 triangles. So you still end up adding 2, regardless of whether it's on the boundary of one of your previous triangles or if it's on the interior. Yeah. So at each stage, we're adding 2. You end up getting 13, and then it's kind of like I suppose, a more continuous version of the pigeonhole principle, where rather than dealing with discrete numbers and putting them into holes, we're kind of dealing with, you have a certain amount of area. If you were to divvy that up somehow into 13 parts, one of those parts must size. It's kind of like you have an interval of size 4 and you partition it into 13 different parts, each of them relating to the area of one of the triangles. One of them must be a certain size. Yeah. Cool. Any questions about any of that? I don't think so. Beautiful. All right, I think that's the end of the presentation.
Awesome. Thanks, Ethan. I'll just stop recording.